Chapter 18, the final presentation. And this one is going to, start off and talk about for quite some time regulation of pumping. And this is not all we're going to talk about. We actually pick up a little bit of development and some other stuff at the very end. But anyway, we start off by talking about regulation of pumping. And to talk about this, we are going to introduce the term cardiac output. And cardiac output is the amount of blood pumped out by each ventricle in 1 minute. And cardiac output is going to equal heart rate times stroke volume. Now, stroke volume is the volume of blood pumped out by one ventricle with each beat, and this is going to correlate with force of contraction. At rest, cardiac output equals heart rate times stroke volume. So heart rate about 75 beats per minute, stroke volume about 70 mils per beat, gives us about 5.25 liters per minute. Now, maximal cardiac output is 4 to 5 times resting cardiac output in non-athletic. Okay, I just completely messed that whole sentence up. Let me start over. Maximal cardiac output is 4 to 5 times resting cardiac output in non-athletic people. This is about 20 to 25 liters per minute. Maximal cardiac output can reach up to 35 liters per minute in trained athletes. Then we have the term cardiac reserve, and this is the difference between resting and maximal cardiac output. And then the cardiac output can change. It can increase, it can decrease if either or both stroke volume or heart rate is changed. And cardiac output is affected by factors leading to regulation of stroke volume and regulation of heart rate. Now this makes sense because, again, cardiac output is stroke volume times heart rate. So anything that's going to regulate stroke volume or regulate heart rate is going to affect, potentially, cardiac output. So this is a very kind of complicated diagram that I'm going to talk about once we're done talking about all this other stuff first. But I just wanted to show it here because we are about to get into it. So, regulation of stroke volume is what we're going to talk about first. Mathematically, stroke volume is end diastolic volume minus end systolic volume. And end diastolic volume is affected by the length of ventricular diastole and venous pressure. And systolic volume is affected by arterial blood pressure and force of ventricular contraction. We have three main factors that affect stroke volume: preload, contractility, and afterload. Preload is the degree to which cardiac muscle cells are stretched before they contract. The most important factor in preload stretching of cardiac muscle is venous return. And venous return is the amount of blood that is returning to the heart. Two things increase venous return: a slow heartbeat and exercise. Increased venous return distends or stretches ventricles and increases contraction force. Next thing we have is, contractility. Increased contractility lowers end systolic volume. This is caused by sympathetic epinephrine release will stimulate increased calcium influx, leading to more cross-bridge formations, or positive iotropic agents increase contractility: thyroxine, glucagon, epinephrine, digitalis, high extracellular calcium. Decreased by negative iotropic agents: acidosis, increased extracellular potassium, calcium channel blockers. And then, afterload is pressure that ventricles must overcome to eject blood. So there's back pressure from arterial blood pushing on the semilunar valves, and that is a major pressure. The aortic pressure is around 80 mmHg, and pulmonary trunk pressure is around 10 mmHg. Hypertension affects or increases afterload. It is affected, but it increases it, resulting in increased in systolic volume and reduced stroke volume. If stroke volume decreases as a result of decreased blood volume or weakened heart, cardiac output can be maintained by increasing heart rate and contractility. And then heart rate can be regulated by three things: the autonomic nervous system, chemicals, or other factors. So the autonomic nervous system does regulate the heart rate. So the sympathetic nervous system can be activated by emotional or physical stressors. Remember we talked about the E's in ANP1 with the sympathetic nervous system: excitement, embarrassment, emergency. Norepinephrine is released. It binds to beta-1 adrenergic receptors on the heart, and this is going to cause the pacemaker to fire more rapidly. And when the pacemaker fires more rapidly, it's going to increase heart rate. And it's also going to lead to increased contractility. Now, with each of these, it's going to cause different things to happen. So the increasing of the heart rate is going to cause end-diastolic volume to decrease because of a decreased fill time. An increased contractility is going to result in an end-systolic volume decrease because of increased volume of ejected blood. Because both end-diastolic volume and end-systolic volume decrease, stroke volume can remain unchanged. Parasympathetic nervous system is going to oppose sympathetic effects, which just basically means that its job is going to be to lower heart rate. But we have acetylcholine hyperpolarizes pacemaker cells by opening potassium channels, which slows heart rate, has little or no effect on contractility. Heart at rest exhibits vagal tone. The parasympathetic nervous system effect is the dominant influence on the heart rate. It's going to actually decrease the rate about 25 beats per minute. If you cut the vagus nerve, it'll lead to a heart rate of about 100 beats per minute. And when the sympathetic nervous system is activated, the parasympathetic nervous system is inhibited, and vice versa. All right, back to this. So we have exercise and a lowering of heart rate. Both of these things, if you remember from the previous slides, are going to increase venous return. So actually, let me discuss this first. So the pink is the initial stimulus. The green is a physiological response. And then the yellow or brownish, whatever you want to call that, is the result. Excuse me. So again, exercise, a decrease in heart rate. Both are going to increase venous return. Both are going to increase end-diastolic volume. This is going to increase stroke volume, and the result is going to be to increase cardiac output. Blood-borne epinephrine, thyroxine, excess calcium, increased contractility, decrease in systolic volume, again, increase stroke volume, increase cardiac output. And then changes in the autonomic, and then CNS output. So we've got two different routes here. We've got an increase in sympathetic activity or a decrease in parasympathetic activity. Both are going to increase heart rate, and that's going to increase cardiac output. This right here should say cardiac output equals stroke volume times heart rate. Chemical regulation of heart rate also occurs. There are hormones. Epinephrine from the adrenal medulla increases heart rate and contractility. Thyroxine increases heart rate and enhances the effects of norepinephrine and epinephrine. And then there's ions. Intra and extracellular ion concentrations like calcium and potassium have to be maintained for normal heart functions. Imbalances are very dangerous to the heart. Other factors also influence heart rate. Age. A fetus has the fastest heart rate and is going to decline with age. Females have a faster heart rate than males. Exercise will increase heart rate. Trained athletes will actually have a slower heart rate. And then body temperature. So heart rate increases with an increase in body temperature. And then when we talk about the final thing, these are the final 3 slides plus the questions and the copyright page. But we're going to talk about developmental aspects of the heart. The human heart is derived from mesoderm, and it begins as 2 endothelial chambers that fuse, and it forms a single actively pumping chamber by day 22. The tube develops 4 bulges, and that's going to represent early chambers. There's the sinus venosus, which is going to give rise to the right atrium, coronary sinus, SA node. Atrium becomes pectinate muscles of atria. Ventricle becomes left ventricle. And then bulbus cordis becomes or gives rise to the aorta, pulmonary trunk, and the right ventricle. I am not going to ask you this. Anything from here I will not ask. Just so you know. And we have day 20 heart, 22, 24, 28. We have bending is continuing at this point. And then by day 35, bending is complete. And we have this structure. That's pretty amazing from day 20 to day 35 to get to this. The heart tube contorts and structural changes convert into a 4-chamber heart by day 35, which is what I just showed. Okay, and then there are 2 fetal heart structures that are going to bypass pulmonary circulation. The foramen ovale, and this is an opening between the 2 atria, so blood can just flow from the right atrium to the left atrium. In an adult, the remnant is called the fossa ovalis. And then there's the ductus arteriosus, and this is going to connect the pulmonary trunk to the aorta. And the remnant is the ligamentum arteriosum in the adult, and this is going to close shortly after birth. I'm sorry, close at or shortly after birth. Okay, and then we have age-related changes affecting the heart. Regular exercise can keep your heart healthy. And then age-related changes include the following: sclerosis and thickening of valve flaps, which can lead to heart murmurs. A decline in cardiac reserve, the heart becomes less efficient. Fibrosis of cardiac muscles, which leads to stiffened heart, arrhythmias caused by conduction system problems, and atherosclerosis, and this may be averted by a good diet. This is your question. Copyright. And that is all I have for you.